Welcome to another series of the Monogoto Developer Program. Thanks a lot for joining in. My name is Lawrence and I'm accompanied by Jan Willem Smeek from SODAQ. And in contrast to a few of the workshops that we had in previous sessions, this is actually a very challenging subject because today we're going to dive into low power of IoT devices. And this is, I would say, a bit more complicated, but this is a vital part of any IoT solution. And therefore, I'm very happy to have with me Jan Willem. He is one of the experts into this field. He's been working in IoT and definitely in this low power IoT for many years already. So thanks again, Jan Willem, for joining in. Maybe you want to say a few more words about yourself before we get started.
Yeah, like Lawrence said, I'm the founder of SODAQ. SODAQ is a company that specializes in IoT. We don't do anything else than IoT. And we spend most of our time working with narrowband IoT and LTE-M. And Monogoto is a valued partner of ours. And yeah, I'm really excited that I could join this workshop and share my knowledge with you.
Perfect. All right, it's great having you. So let me share my screen and we shall slowly start giving people a few more minutes to tune in. I already see that some people are joining in all the way from Colombia. Great to have you here on board. Yeah, feel free to send a message. I'm curious where you are from and who you are. So feel free to use the chat feature, and there's also a Q&A section. Feel free to use it. If you have any questions during the presentation, you can directly write your questions there and we will address them all at the end of this session. So today will be all about low power modes. And well, we just had a short introduction. So for the ones who don't know me yet, so my name is Lawrence. I'm the developer community manager at Monogoto and the host of this workshop series. So today's agenda, so we start with a bit of information on power profiles, giving you some insights into the different operational modes of an IoT device. Then I'd like to give the word to Jan Willem, who is going to share some information about designing an IoT application for low power. And he will end with information about real-world scenarios. And this is actually what I'm really excited about, because we're not only talking about the theory and about the data sheets, we actually back up all the information with some actual real world scenarios. And like I mentioned, so this topic is very challenging. So if you have any questions during this session, feel free to post them in the chat or in the Q&A. And later on, if you re-watch this workshop, or if you have any further questions later on in this process, then I would warmly invite you to engage on our forum, which is the central place for anyone who receives support around Monogoto, but also to connect with fellow IoT developers. So power modes, there are 4 different modes of operation that you can think of. Let's discuss all of them. And well, the very first one is RRC, connected. And this is the most obvious one when thinking about IoT, because this is actually the part where you actively transmit or receive data. And well, I would love to stress already now at the beginning that this is not the part that's low power. Sending or receiving data actually consumes a lot of energy. And if you do that too frequently, then it will drain your battery. And we'll back this up with a bit of data later on. So the second mode is what we call RRC idle. And in that mode, the device is not sending data, but it is listening for incoming messages. And you can listen continuously, allowing the network to send messages to the device. But what's more common is that you have something that's called discontinued reception. And it means that the device regularly pages, what we call pages the network, to see if there are any pending messages from the network. And the default duration is 1.28 seconds. So then every 1.28 seconds, it pages, checking if there are any messages from the network, and then it goes back to sleep. And after a second, it pages the network again. And the beauty of new novel technologies is that you can extend this sleep period. So instead of 1 second, you can lengthen this period with, I don't know, let's say a couple of more seconds or even a couple of minutes. So you can extend this discontinued reception interval. And it can even go up to 43 minutes. So this is already much more battery efficient compared to RRC connected. And when you want to get the energy drain even lower, then you can put your device into PSM or power saving mode. And the part there is that you can put your device into deep sleep, or what we call a hibernate state, for a very long interval. But it's important to know that during this PSM, the device is not able to receive any messages from the network. And then finally, obviously, you can also completely turn off the radio, and that obviously consumes the least energy of all of the 4 modes. And to back this up with some data, and this is the data that I found in the data sheets from the u-blox SARA modem. And later on, Jan-Willem even have some real data actually to show about the energy consumption. But this is what I found in the data sheets. And it shows that sending data is, I know that's somewhere between 100 and 300 milliamps. So that's not low power at all, and it consumes a lot of energy. So then if you look into RC idle and have these paging windows of 1.28 seconds, then it consumes about 2 milliamps. And if you extend that paging window to 20 seconds, then look, you have about half that amount of energy drain, about 0.9 milliamps. And if you then activate power saving mode, then you can even get the energy drain down to 8 microamps. And I want to elaborate a little bit on these different power modes. So the first one is the DRX, so the discontinued reception. And how it normally works is that the device boots and it starts to attach to a network, which can be quite energy consuming. Then it starts sending its first messages, and then it starts to activate, or let's say, then it enters the active time. And the technical term for that is T3324, and that's the duration where it frequently pages the network checking for incoming traffic. And then up to a period of time, then it sends a TAU, which is the tracking area update, basically sending a message to the network saying, hey, I'm still here. I'm still actively using this network. So if you then extend this paging cycle, then it looks something like this. So again, it boots up, it sends a message, and then it goes into a paging time window, which is kind of a set interval where it frequently checks with the network for incoming traffic, and then it enters the EDRX cycle, which is a period of time where it's in sleep mode and cannot receive any messages. And once these timers exceed, then it starts paging again. And this is a cycle that loops, and that together forms then the active time. And then if we stress it out a little bit more, then we can include this power save mode into this overview. So the active time contains the paging time windows as well as the EDRX cycle, and it loops for a certain amount of time. And that amount of time you can define as the active time. So you can set that using AT commands. And once the active time exceeds, then you can actually put the device into PSM mode, where it reduces the energy even further. And this together is called periodic TAU. And that's another variable that you can set using AT commands. So understand this, and this is a little bit hard to understand. And I understand if you're still puzzled, but worry not, because they're basically 4 variables that I'm explaining here that you can set, which is the paging time window, the EDRX cycle, the active time, and the periodic towel. So far, a little bit of theory, and I'd now like to give the floor to Jan Willem, who's going to highlight and explain more about actually designing a low power application.
So the first thing we need, if you design something low power, is an instrument that you can measure the actual power usage. We at SODAQ, we're very fond of the COITEC OT. It is a brilliant tool. It's very easy to use. And I'm using it on all the charts that I will show on from here. The link to the OT is in here. I've done some tests on our SODAQ AFF board, which uses the LTE-M technology. You can stick in a Monogoto SIM, so as you can see in the picture there, and you can start measuring what the actual power consumption is. So if you want to design a low power device, rule number 1 is sleep whenever you can. Low power devices that are intended to work for years on batteries, or use, for instance, renewable energies, maybe a little solar panel, they need to sleep 99.999% of the time if you can. Because if they sleep, they use only a few microamps. What you see in the picture here is our SODAQ Sarah board, so the board that you can buy in our web shop. On the SODAQ support pages, there is a little Arduino sketch that you can load on the device to illustrate how the deep sleep cycle works. And in this case, the device is in a deep sleep for 5 minutes. It wakes up and flashes an LED, and then it sleeps again for 5 minutes. What you see here, the measurement of the OT shows that during that sleep cycle, the actual 5 minutes there, the average power consumption is only 13.8 microamps. In fact, it has not much to do. The 13.8 microamps is basically the clock that is ticking there, and the interval timer to wake it up after 5 minutes to flash the LED again. But this power consumption of 13.8 microamps, you see over a 5 minute period of time, it's only 6.77 nanowatt hours. If you compare that to all the other work that you're doing, this in most of the cases can just be neglected. Step 2, if you design a low power IoT device, is only work when you have to. Now, what kind of work do you want to do? For instance, you want to take a temperature measurement. What you see in the OT screen here is the device sleeps, it wakes up, it does a temperature measurement, and then it goes back to sleep. This temperature measurement is of a very short duration, so you sleep all of the time, but to do a temperature measurement, you only wake for 40 milliseconds. During the 40 milliseconds, the maximum current was only 1.3 milliamps, but the total energy to take such a temperature reading is only 54 nanowatt hours. Again, you can calculate in your power budget what the impact is. For instance, if you have a battery that has 100 milliamp hours, you can easily calculate that over the lifespan of the device, maybe the temperature measurement is only 1% of your overall power budget. The third step is communication. Communication takes a lot of power, so you want to communicate as briefly as possible. You only open the communication channel when you need it. You send the minimum amount of data. And when I say the minimum amount of data, people often make the mistake to use high-level protocols like MQTT over a TLS connection or HTTPS. Well, those things, they are not very smart in a low-power IoT device. What we do at SODAQ is we send a UDP datagram and we receive a UDP datagram. So 500 bytes up, 100 bytes down, and that's it what we do here. And that's exactly what you see in the chart here. I'm sending and receiving the data. The total duration from what you see here is the device wakes from sleep, it reattaches to the network, it sends a message, it receives a message, all in 5 seconds. The maximum current that has been seen drawn here on our 5-volt battery is 176 milliamps. So the total footprint of this actual sending of the message is 153 microwatt hours. That, of course, is under good conditions. You will see if the network coverage is not so good, this may be a little bit more than that. But so typically what we say, the sending of the message would take between 150 and maybe 200 microwatt hours. So how does that work? Basically, what we say is you can have two types of devices. You can have a static device. Think of, for instance, a smart meter, On a static device, it's quite easy to send regular messages because it doesn't change cells. So you wake up, you send a message. So that's quite easily doable. Also, concepts like EDRX, whereby the device is paging the network regularly, they work best in a static device. Because the static device, when you wake up, you listen, you are in the cell that you were when you went to sleep, and therefore the paging works. If you have a device that is on the move, chances are that your EDRX doesn't work at all because you're paging. You won't see anything on the network because you have moved already to the next cell. So therefore we say, in principle, forget about EDRX on a mobile device. On a mobile device, the column on the right, we typically send messages once an hour or even longer time in between. And we initiate the communication by the device, not so much by the server. So in this slide, sorry, two things have been swapped. On a static device, the server could initiate communication if we use EDRX. On a mobile device, we typically always let the device connect to the server. So in this flow, basically what we say, we switch on a device, we take up to 3 minutes to do a first time connect to the network. Then we are connected to the network, and then we can send the message. And then, of course, the next message will be much faster because the device will remember the mobile network operator, the cell, the band where it's in, and everything in there. So that's typically what we're doing. So talking about power consumption, like I said, static devices are easy. The static device behavior could be controlled from the cloud. We could use EDRX in here. And it all depends on the latency. So let's say we want to control a smart meter readout. So the network sends a message to the device, please send us the last readings. If we want to get that information within 5 minutes, we need to make sure that the device is paging the network every 5 minutes. And the rest of the time it sleeps. So we've simulated that. And in the next slide, you see the power profile for such a kind of paging. So what you see in here is a 5-minute EDRX paging cycle. So the device is in deep sleep, it wakes up, it pages the network and goes back to sleep, wakes up, goes back to sleep, etc., etc. After 54 minutes, it has to do this tracking area update. So what I've shown you here is an OT snapshot of the period of 1, 2, 3, 4, 5, 6, 7, 8, 9 pages and a tracking area update. This whole process takes just over 54 minutes. And as you can see, the average power consumption was only 47.5 microamps. So you could have a device that has an average power consumption of 47.5 microamps, and only at the time you want to have a proper readout of your meter reading, it probably is going to use 200 microwatt hours for just the readout of the meter reading. So here you see that actual tracking area update. The tracking area update just takes about 2 seconds because in a static device, we are in the same cell. So it wakes up, connects to the network. The network says, oh, good to see that you're still there. And the whole thing shuts down again. And this tracking area update takes as little as 70 microwatt hours. Now, we make it a little bit more complex. SODAQ has a nice series of tracking devices that you can buy from us. We have a solar power device, we have a rechargeable device, we even have a device that has 3 AA batteries. And these devices, they are designed to run on the battery powered, for instance, somewhere between 3 and 10 years on just a set of batteries. So what we had to do is we had to design something that is extremely low power. So contrary to the static device where the tracker could be, this device can be anywhere when it first connects to the network. So what you need to do is when you switch on the device has to scan several bands, establish a connection, and this may take up to 3 minutes. We have to live with that. During the 3 minutes, it may use between 50 and 100 milliamps. Now, I simulated that, so I wired up the OT to one of these tracking devices. I did a first time power on. It's powered by this 4.5 volt battery pack, so the 3 AA batteries. But what you saw, because we are in good network conditions, it only took 19 seconds. So it can take as little time as 19 seconds, but it could also take 3 minutes if the network coverage is much poorer than that. As you see in this scenario, during the 19 seconds, the maximum current was 151 milliamps. So not too dramatic at all. And the total energy usage was 493 microwatt hours. So what you can say, the first time attach takes the power of about 3 times what a normal sending of a message takes. But like I said, if you're in poor network conditions, if the signal quality is poor, it may take much longer. Now, after we are connected, the next message can just be sent in just over 5 seconds, between 5, 6, 7, 8 seconds. So the device is in deep sleep, it wakes up, it reattaches to the network, it sends a message, it receives a message, and it goes down again. Like I said, somewhere between 150 and 200 microwatt hours for just sending a single message. And like I said, this is a snapshot of the SODAQ track device in deep sleep. It only uses 13.2 microamps continuously. One thing I need to tell you here is that the SODAQ track is a device that uses the Nordic NRF9160 microcontroller and LTE-M module. And we found that that is probably the most energy efficient LTE-M module in the market. So it's this combination of the module and the microcontroller in one. So sending LTE-M data is basically reconnecting to the network, sending a message. And if we do this according to the book, we are connected during the RRC connection interval, which duration is dictated by the network. In Europe, it's typically 16 seconds. And then after that, it will have a little paging interval, the IDRX interval, which you can set yourself. And then you will go back to sleep or optionally enter the EDRX mode. So this is how the network would like you to do it. So I wired up the device to the OT, and we wired it up the way that the network would like to see it. We sent the power save mode command, as you can see, the AP SMS command, in which you have the timer for the paging window, the T3324 parameter, is the second parameter you see here. In binary, it sends 1010 as binary. As we all know, that means 10, but there is a multiplier by 2, so that means 20 seconds. So what you see depicted here is the sending of the message, which takes about 500 milliseconds. Then we have to sit out the RRC idle period, which is somewhere between 50 and 100 milliamps continuously. And then we need to do the paging, which could be up to 20 milliamps in the paging window. So what we were asking ourselves is, okay, we send a message that only takes 100 to 200 microwatt hours, but we need to sit out the whole bloody RRC cycle. And that RRC cycle may take as much as 2 milliwatt hours. And then we do the paging. Now, initially, I thought that paging meant that you need to do paging to be able to receive a message. But that's not true. You can receive messages during the RRC idle period. So why on earth do we need to do paging after the RRC idle period? So the first thing we did is actually drop the RRC, the idle period. Why we dropped the paging window and we only run the RRC idle period. But then again, why do we run RRC idle for 16 seconds? Yeah? Most people think that we need to go through this whole PSM cycle. So we need to do what the telcos dictate to us, that we do RRC, we do paging, etc. But on a low power IoT device, we found from our experience that it's way easier not to sit out the whole cycle, just disconnect when sending and receiving is completed. So in the next slide, you will see that I depicted here just the sending and receiving of the data. We sent the message, we waited for 1 second, we got the feedback from the server and we shut it down. What you see in here is the 150, 170 microwatt hours for sending the message. We dropped the whole RRC, forget about the RRC, forget about the paging, forget about the tracking area. We just go back to sleep. We shut off the modem after sending the message. Now, this is not according to the book, and network operators may not like it if you disconnect and connect too often. But what we've seen is that connecting 6 times per hour is acceptable by all the network operators. And for a low power device, who needs to send more than 6 messages per hour? So you basically, in the design that you're making for your low power device, can we go back 1 slide, is if you want to send more than 6 messages per hour, sit out the full RRC cycle, do the PSM, play according to the book. But if you send 6 or less messages per hour, just drop the connection. just step out and go to sleep. Whenever you come back on the network, it's way quicker. And by applying this method, we found that we can be up to 10 times more power efficient than playing the whole thing according to the book. So what we did, and we're gonna show in the next slides, we come up with some real life scenarios. What we say is that in the time that your radio is on is relevant. So as we say, we send a message, we switch off the radio, and then we wait, and then we send the next message. So what we have done in our device and in the software that we created is basically we keep track of the time that the modem, the radio, is on. And we include the radio in the payload that we're sending. So what you see in this example is we have a good network coverage. The signal quality is really good. We are in a no network. We move a little bit so we don't go too far. And in the blue box that you see on my screen here, there's the two variables that we include in the payload. So what we say, every message that we send, we increase the counter. Even if the message attempt fails, the counter goes still up. So we use the counter to see for any failed messages, and we keep the modem on time also in the payload. Now what you can see here, last message was 160, the message after is 161, and our modem on time went up by only 8 seconds. So that shows that from sleep, waking up, sending a message, and go back to sleep took less than 8 seconds. This works well because in the right-hand column, you see the received signal strength. The RSIP value here is 44, which means that it's a really good network. In fact, to translate this to dBs, you have to deduct 140, but these are the raw values that we get from the Nordic module. So a value over 30 is a good signal quality, and that's why you see that this works really well. So every message that we send, the counter goes up by about 8 or 10, and that you can see because if you divide the modem on time by the number of messages that you send, you see that the average modem on time was about 12 seconds per message that we're sending. With this setup, in this scenario, your battery is going to last forever. Really, we're gonna run for at least 3 years on a set of batteries. But in the next scenario, we make it a little bit more complex, is we still have good coverage when we're crossing a border. So what you see in this slide is actually we put a device on the plane and we sent it to the UK. We've implemented a clever flight mode on our device. So when it's on the plane, it's not sending. And you can clearly see in the third column is the mobile network country code. So from 204, which is the Netherlands, we go to 234, which is in the UK. You can see that between 313 and 314, no messages are missing. So it didn't attempt to send a message on the plane. And the time that it took to send the message is about 43 seconds, which is really good, considering the fact that from that point on, it uses 8 or 9 seconds again to send locally. So the transition, meaning to scan for a new network in a new country, we went from one operator, T-Mobile in the Netherlands, sorry, Vodafone in the Netherlands, to the 10, I don't know what 10 in the UK is, I think 10 is Vodafone in the UK, but two different networks still in a very short period of time. But things can be worse. You can also say, okay, we have good coverage, but we go from one continent to the other. In the previous scenario, we probably stayed in band 20, so that was easy for the modem. It was in band 20, it went to the new country, it scanned band 20 again, so the time to connect was really, really short. But now we go to a different continent, so we have to work at different frequencies, so we have to scan for a much longer period of time. You can see that in the next slide. We flew to the US. The first thing you see that after between message 13 and 15, we lost a message. So it landed in the US. It tried to establish a network connection, but it failed. The next time it worked, but then after that, it still struggled. So you can see from the last successful message in the Netherlands to the first basically inflow message in the US, the total loss is more than 400 seconds. So that's the penalty for crossing borders. Once it has established itself, you see in the blue box, it again takes about 8 seconds between messages for every new message that you're sending. But crossing borders put quite a penalty on your battery. And as you can see on the right-hand side, the signal strength is pretty good. So it's not about the signal strength, but it's totally about the fact that you're in a complete new network. Now, what if you have a very poor network coverage? What is happening? And what you will see is you'll have packet loss. The network coverage is so poor that it fails to send messages. So in the next slide, you see we are in the US. We're in the middle of freaking nowhere trying to send messages. On the right-hand side, you see the RSRP is 4. Well, the lowest value that you can probably send messages is an RSRP of 3. So we are 30 to 40 dBs below what we used to with a good signal quality. And it shows in the figures that you see here. You see that, that there's 100 or 500 or 400 or 400 seconds between the messages that we're sending. So the modem is really on for a long time, struggling to send messages. We see messages 119, 117, and 115 are missing. So it's a really borderline type of sending of messages. So again, that eats in tremendously on your battery life. So all these variables you have to take into account when you're building and deploying your low power devices.
So to conclude the story from Jan Willem, well, let's get back to the 3 principles. Well, first, it's sleep as much as possible. So a device that sends data frequently is not low power. So the core principle, you have to sleep as much as possible. Work only when you have to. So be clever when you design or program the triggers that activates the device. And also communicate briefly. Just keep the protocol simple. Try to simplify the whole communication to reduce the communication period. Then we go into EDRX. Well, we've seen that EDRX, we only have to use it for applications where the server initiates the communication. So when a device always initiates the communication, then it's not needed to use EDRX at all. And as an example, as Jan Willem mentioned, is that EDRX doesn't really work well when devices are mobile, because then it might go to a different cell, which makes it very challenging for the network to find the device and send the message accordingly. So EDRX mostly works for static devices. And also what we've seen here, that PSM or power saving mode, which is a feature that many are talking about, but apparently that's not really a holy grail. And so we've seen that this works when you're sending, let's say, at least 6 times per hour. Then PSM is actually a mode that we have to use. But if you're sending data, let's say every hour or less, then it's better to completely shut down the modem in many cases, because that will actually that's actually much more battery efficient. And this is quite a lot to take in all at once. So I did write a full tutorial about how to use your devices, how to use the low power profiles. There's a very detailed instructions on how to set EDRX and PSM. So I warmly invite everyone to have a look at the documentation, to search for the page low power modes, EDRX and PSM. Because to activate these modes, it's merely sending a few AT commands, instructing the modem to go into these specific low power modes. And then you might ask, okay, so how does Monogoto fit in this whole story? Well, Monogoto is a MVNO, or a mobile virtual network operator, which means that we operate the core network of IoT solutions, being responsible for device management as well as data routing. So we concentrate ourselves on the virtual parts, and it means that we don't own or manage physical infrastructure. But instead, we collaborate with 500 or so networks, allowing all devices with a Monogoto SIM, which can be either plastic SIM or an eSIM soldered onto your PCB. And it can, when you have that Monogoto SIM, then you can use about 500 operators around the world, from AT&T to Vodafone to T-Mobile. And our aim is to have at least 2 networks that you can choose from, and in many cases even more. And as we've seen in the presentation, is that the network quality is actually a key factor for reducing the energy drain, because you need to have proper coverage, and otherwise it keeps searching and scanning for networks, which is a very power inefficient process. So we always aim for giving you multiple options in choosing your specific mobile operator. And then diving into our platform itself, well, like what we aim, and how we do so is that we have a very intuitive console to manage all your connections. So you can manage individual connections by managing the SIM, or you can group specific SIMs and manage them all together. And the beauty is that you can use the console, but you can even manage all of these settings using our APIs. So you can fully embed our device features and all of our functionalities in your platform of choice, and kind of skip the whole part where you need to use our graphical user interface. And the part that I personally really like is that you can very easily integrate Monogoto into different platforms, and you can define specific alerts. For example, when the SIM connects for the very first time, you might want to get an alert, either on by receiving an email or by creating a custom integration to your platform and giving a notification that an event occurred. But it can also, when you, let's say, surpass 100 MB of data, but you can also have an alert when devices are offline for a certain period of time. And finally, there is a set of more advanced features, for example, improving the usability or security. So one of our popular advanced features is VPN tunneling, kind of increasing the security of your IoT solution as a whole. So there was a lot to take in, and I see that there are a few questions in the chat, which we are going to address in a second. So if you're still puzzled at the end of this presentation, then feel free to head over to our forum and engage with Monogoto experts. You can ask any question, and there's also a ton of documentation and resources available on our documentation website. And it almost concludes the third workshop this far. I will send you an email later on with the recording, and that contains also a link to the previous sessions. And next week we are here again, and I'm joined by Ubidots, and there we are diving into integrating and acting on IoT data. So we'll explain more about UDP, TCP, MQTT, kind of giving the advantages of all of these protocols. And we're not only diving into uplinks, so messages initiated by the device, but we also dive into messages that are initiated from the network and discuss the implications there. So thank you so much for listening. And let's start looking into some of the questions here. If you have any more questions, feel free to drop them in the chat or in the Q&A. Allowing us to discuss them right away. Yeah. So I see a first question from Sokulo. At PSM modes, can that be activated by sending an SMS to the device itself? Well, the beauty is you can. Okay, so there are two things you need to keep in mind. So first, when a device is in PSM mode itself, then it cannot receive any messages or any data from the network. So a device in PSM mode cannot receive any SMS or text messages. But what you can do, and that's basically how all the firmware is programmed, is that you can basically await a text message to be received, and when that is received, then you can program it in such a way that as a response it activates specific AT commands. For example, the device going into PSM mode.
Shall I take the next one, Lawrence?
Yeah, please go ahead.
Yeah, it's a good question from Tan KY. we were talking about the UDP datagram and quality of service. Indeed, there is no service guarantee for UDP. You send a UDP datagram and you never know if your UDP datagram arrives. Well, when I first started working on the internet, and that was in 1991, so that's about 31 years ago, it frequently happened that UDP datagrams were dropped, which at that time was a bit of a problem. Now, what you see with all the fiber optic links that we're having, the quality of the internet overall has improved so much that typically we don't lose UDP packets. So the only vulnerable part in which sending data is the radio network. Once it lands at the Monogoto core, you can be sure that the UDP message arrives at your server. No worry about that. So from the viewpoint from the device, a device sends a UDP message. And what we do is we always make the server respond. So the device sends a message to the server receives the message and sends a backlink back to the device. And this can all happen in a time frame of about 500 milliseconds. The device sends and the device receives. If the device doesn't receive a message, you can make the decision of retrying. So you could build a very simple mechanism. If I didn't get a reply, I just resend it. And then you could put, let's say, a value in there that I retry once, I retry twice, and then I give up. And then we do it again. The next time we wake up, we send the next message. So that is basically the architecture that we have in low power devices. If you compare this to MQTT or HTTP, that's all TCP/IP based. So those are stateful connections. And indeed, in a TCP/IP connection, it is actually the protocol that is taking care of this. But this comes at a price. The penalty is quite high. With UDP, I send 500 bytes up and 100 bytes down, so that's 600 bytes of data traffic. If I do the same with MQTT over a TLS connection, I probably send about 16 kilobytes or 20 kilobytes. So there's a huge penalty for these high-level protocols. And that's why we say better use the simple protocols, because then your session time is really short. You can disconnect, you can go back to sleep, and your battery will last forever. And like I said, with a simple implementation of a retry when you don't get a downlink message, UDP, in our opinion, basically offers the same service quality as you would get from these higher level protocols.
Perfect. So I have one more question for you, Jan-Willem. So in the last slide, you showed that there are actually many messages missing because of poor network quality. So if you would, and if any of the developers here would be in such a similar place, like what is then the recommended approach? Do you keep trying until it succeeds, or are there some technical the procedures that you can go into?
Well, the first thing is that we would never try more than twice. If you do 2 attempts and you still don't get your downlink message, it means that there's a serious problem, so you give up. But as these low power IoT devices are often for, let's say, sensing or tracking, what you can do is you can basically store the content of your message locally, and the next time you have a proper connection, you send all the registered data that you have. So basically, if I can't send the message today, I send the same data tomorrow. And then on the other side, on the server side, you still have all the information that you want to have, maybe with a little time lag in there. But it all depends on your application, how critical it is for the information to be received.
Perfect. Thanks. Final question before we're going to conclude. Is there any further recommendations you want to give any of the listeners, Jan-Willem?
Well, like I said, use a tool to measure. And we gave the OT as an example. There's a lower cost power profiler tool that Nordic is selling that costs about maybe a quarter of the price of the OT. So that could be another approach to go. So if your budget is a bit tight, you might go for the Nordic device. If you have a bit more money and you intended to use it for a long time, you could benefit from the features and the user friendliness of the OT. But you do need a device to measure, because if you don't measure, you don't know. You may think by following the data sheets that what you're doing is power efficient, but at the end of the day, you don't know if you don't measure.
All right, so make sure that you have a tool to measure the power profile of your end devices. Great. Thank you so much, Jan-Willem. It was a great presentation together with you. Very happy with how this turned out. So thank you so much. And I would love to see everyone again next week at the same time, where we dive into integrating and acting on IoT data.
Thank you all. Bye-bye.